Good afternoon, good people. Today I would like to show you, we'll be looking at the Baeyer-Villiger oxidation rearrangement. We'll be looking at the what? At the Baeyer-Villiger oxidation or rearrangement. So in this reaction, what basically happens here is that you've got a ketone that you start with, right? Which you treat with a peroxide, in this case hydrogen peroxide. Then what does that give you, right? That gives you an ester. Okay, now for example, now like here, this reaction can take place in the presence of an acid, or it can take place in the presence of a base, right? Now let's take an example here whereby now like we start off with a cyclic ketone. So what then do we get now, like when we do this, when we carry out this reaction, right? In the presence now, for example, of what we refer to as a peroxy acid. A what? A peroxy acid, right? Which is nothing else but the equivalent of a hydrogen, what we call like peroxide. That is, this one, it's more like an organic chemistry peroxide, if I were to put it that way. Then what does it generate? It gives us what we refer to as a lactone. A lactone is nothing else but still an ester, right? But what kind of an ester? It's a cyclic ester, so to speak, right? So the most important thing for us as organic chemists that we always stress, it's always about what? The mechanism. How does this reaction actually take place, right? In terms of the what? Of the mechanism, right? So in this case here, as I've already indicated to you that like we start off with a ketone. We start off with what? With a ketone. Let's look at this at the ketone. We've got this here, R. Let's call this one the other R, like as the R prime, right? There's a lone pair. There's a lone pair here. Now, so as organic chemists, we are always interested in our functional group. So the functional group here, it's your C double bond O that depicts what? A ketone, right? So that's where we need to be looking at, right? So for example here now, like if I look at my oxygen atom here versus my carbon atom here, these are bonded together, right? Via a sigma bond and a pi bond. So if we look at the sigma framework, then we know that like in the periodic table, oxygen is much more electronegative as compared to what? As compared to your carbon atom. And therefore, because of that, it has the capability of pulling the electron density towards itself. That is via the sigma framework, right? And when it does that, it assumes what? A sigma negative charge. And as such, the one that is losing the electron density will be your carbon atom here, right? Then your carbon atom, it loses the electron density to become what? A sigma positive, like so to speak, right? Now, right? What basically happens is that now, like, if for example now, like we are going to treat this, let's say now, like in an acidic medium, we treat it with an acid, which is H plus, right? So what is it that is going to happen? Automatically, I've already shown you that like this one will assume a sigma negative state, this one will assume a sigma positive state. So now like logic tells us that like now like this H plus can never come over here. There will be repulsion. So this H plus will come over here, will come and act like in this action side. So how does that react? Then the lone pair from the oxygen atom, it goes out to pick up, that is with both, what we call like with both electrons, right? So it's two electrons, hence I've got a full arrow in that case. So what is it that I form here in this case? Then I end up with oxygen, right? This is R prime, this is R, and a new bond to what? To hydrogen. with only one lone pair that is left in this case now. Now, what has happened now, like hydrogen is no longer positive because it has gotten what? Electrons. Then oxygen was neutral in charge here. It has picked up a positive species and therefore oxygen will become positive, right? In terms of charge, because it has lost what? It has lost electrons, like so to speak, in this case, right? Now, what is it that I formed here? What is it that I formed here? If I look at here, I've got a ketone. What do I have here? Yes, RR, double bond oxygen, double bond oxygen. And then here, there is an extra proton. Therefore, this becomes what we refer to as a protonated ketone. A protonated what? Ketone. A protonated ketone. You like? That is a ketone that has acquired a positive charge. Isn't it? Now, with this oxygen here, right, being positive and also, right, double bonded to this carbon atom, then you've got a double bond here, which is a source of electrons. And then remember, electrons are negative in what? In charge. And therefore, they will always be attracted, right, towards the positive. So as a result, now, like in this case now, like we form what we refer to as a resonance structure. A what? A resonance structure. Then we generate oxygen here, this here, this now, lone pairs, and a single bond here now. This, that here, this is R prime, this is R. Can you see that now? Ne? Now, what is it that has happened here? Is the fact that now, like, between your oxygen and your carbon atom, oxygen is much more electronegative than carbon. That's number one. Number two, oxygen is bearing a positive charge. That is number two. And therefore, oxygen pulls the what? The electron density towards itself. Right? Right? Then now, like, to stabilize the positive charge. Now, what about this carbon atom now? The carbon atom now, like, has lost this pair of electrons, and as such, this carbon atom becomes what in charge? It becomes positive. Then now, like, we end up now like with two structures, you see, and then these structures will now be referred to as the what? As the resonance structures. As the what? As the resonance structures, where each structure will be referred to as a resonance hybrid. Now, between the two resonance, what call like hybrids, which one am I going to continue with going to the next step? Right? I will continue with this one. I look at the atoms, that is the actual atoms that are bearing a positive charge. In this resonance structure, oxygen is bearing a positive charge. In this resonance structure, it is carbon that is bearing a what? A positive charge. Now, carbon, it is said that carbon can better accommodate what? A positive charge, right? As compared to what? To oxygen. And then now, like, then logic tells me that now, like, I will have to continue with the one that can better accommodate what? A positive charge. Now, what am I going to be left with here in this case? I'm left here with H bonded to O, this bonded to R prime, this bonded to R, and there's my lone pair. There's my lone pair. That is beautiful. I love this. Right? Now, there's a positive charge down. Right? So, what is it that I have done here now? Like, I have formed an electrophy. I have formed an electrophy. And this now, like, becomes my electrophilic center in this case. And then now, like, it is now ready to be what? To be attacked by what? By, let's say in this case, I'll take my organic, what you call like my peroxy acid. There we go. This here. This is just an equivalent. You can see HO single bond O as in peroxide. But in this case now, like this is C double bond O and let's say R there. right? Now, this peroxy acid, this peroxy acid, this peroxy acid, right? Peroxy acid. Then it comes in here now, like as a what? It comes in as a nucleophile attacking what? An electrophile. Then what then do we form here now? We form the species. This is H, this is O, this here, this is R prime, this is R here, and a new bond now. To what? To oxygen that is bonded to oxygen that is bonded to C double bond O that is bonded to R, and this oxygen is still bonded to its hydrogen atom. Then we are only left here with one lone pair. Now, if this oxygen was neutral in charge and then now like it attacks a positive species, what does that imply? That implies that now like this oxygen atom now like will therefore become positive in charge. So in this case now like we have our oxygen atom that is positive in charge and that is bonded to hydrogen, whereby oxygen is in group 6 and hydrogen is in group 1. The vast difference in terms of electronegativity is too much, and then oxygen will therefore surely pull these electrons towards itself, isn't it? And then what will this form now? The hydrogen is going to fall off as H plus, right? Then what do we generate in this case now? We generate H, O, this, in this case, R prime, and then this is R, then this one is O, this is O, this is C, double bond O, this is R. Lone pair now, lone pair now, lone pair now, lone pair now, like that's beautiful. Then there's a lone pair in that case, right? Now, if now we come over to the to our organic peroxide. So with peroxides, the bond between this oxygen and oxygen, right, it's easy to break. Are you with me? Right? So once this now like, once the structure now like, because this oxygen and oxygen can easily break with one of this, with this single bond coming over to the other fragment, to the other oxygen atom, then this oxygen now like is losing these electrons. Immediately there's going to be a shift there. There's going to be a rearrangement there of the R group, right, to the next what we call like oxygen atom. Then eventually, what am I going to be left with here? In this case, then I'll be left here with H bonded to O1212, bonded to carbon, bonded to R prime, bonded to oxygen that is bonded to R1212. And then what does that imply now? Like this carbon atom in this case now like has lost these electrons because of that rearrangement, where the R moves position to the what we call like to the oxygen atom. Then this carbon atom therefore becomes positive in charge. And then what else? There is going to be my byproduct. My byproduct in that case will be my R, C double bond O, and then bonded to O121212 minus my what call like RC OO2 what call like minus. And then what happens now like is in this case now like oxygen single bond, then there's a charge. What do we think of? We think of resonance. This brings in these two electrons here, then we get a resonance structure in this case forming O double bond carbon bonded to OR, that side, that R prime this side, 1, 2, now there's only one hydrogen, isn't it? I mean like hydrogen there. Then oxygen has lost those electrons, it becomes what in charge? Positive in that case. Then you've got another set of resonance structures in this case. Now, between these two structures now, like which one am I going to proceed with? Then now like here I want to form an ester. The structure that resembles my ester between this one and this one. If I look at my ester, I've got R prime. I've got R prime, I've got a bond to C double bond O, a bond to C double bond O, then to oxygen, double bonded to oxygen. Then on the other hand, I've got my OR as compared to that one. Then I'll proceed with this one. So with that one, what will happen in any case, this oxygen now, like, which is bearing a positive charge and more electronegative than hydrogen, will simply take away the bond pair. Then with that hydrogen falling off as H plus, right? As H plus, that can combine with that carboxylate to generate your RCOOH, that is your carboxylic acid. Then here, I will now be left with my ester R bonded to C, double bond O, 1, 2, 1, 2, bonded to O, this R. Then I have formed my what? My ester. If I wanted to, then I could even show that one, R, C, double bond O, O, which was minus, then getting that H plus here, then you get this carboxylic acid, right? So this is what we mean by a Baeyer-Villiger oxidation rearrangement, like so to speak. All right? Thank you very much, and I'll see you tomorrow.